Good afternoon, guys. We are going to look at real zeros of polynomial functions today. This kind of builds off of what we did with 3.1 yesterday and from the beginning of last week. This is this video will encompass half this set of notes. I'll release the second video later on today. I want to try to do one full set of notes each day to get us back on track and catch us up where we need to be so that we can complete this course on time. I'm still awaiting word from both EKU and Perry Central to kind of coordinate when we will actually end this class, because we do have to cover the content. That's not an option with the university class. This is also the 5th time that I have sat down to record this video. That's not an exaggeration. The previous 5 times, about 2 minutes in, the video, or the audio rather, is, I don't know what it's doing. It sounds like a robot almost. So hopefully this will work. I've rebooted everything, made sure all the updates are right. So anyway, we're gonna try this again. So let's go. Here we have the everything that I just skipped over. Kind of talks about the division algorithms for polynomials, and we're going to get into that a little bit more later, so you're welcome to look at that if you'd like, but we will cover that in more detail later on. The only thing really that you need to know for today is synthetic division, and if you don't recall how to do synthetic division from Algebra 2, hopefully what we cover today will refresh your memory. I do encourage everybody to watch both videos today. We'll have a Zoom class tomorrow, and during our Zoom class, I will answer all the questions that you have, because this content for today specifically, it's not difficult. This is one of those concepts, though, that is much easier taught in person because we can go a little bit slower. I can answer your questions. I'm doing my best to try to anticipate what questions you may have as I produce these videos, but that's not always the easiest thing in the world. So I have a feeling there will be a lot of questions generated from what we're covering today, and we'll address those tomorrow in our Zoom class. The first thing we want to look at is the remainder theorem. And the remainder theorem just simply allows us to look at some polynomial. If we're going to divide it by a linear factor, whatever the zero is of that linear factor, if we evaluate the polynomial at that zero, the solution is our remainder, as if we had done the division. And I'm going to show that to you here with example 1. We have the polynomial x cubed minus 4x squared minus 5. If I were to divide that polynomial by x minus 3, what would the remainder be? The way we do that is by using the remainder theorem. We simply take this linear factor and we solve it for x. So if we set it equal to 0, then we get that x has to be equal to positive 3. And we can take that value of positive 3 and we can evaluate our given function at 3. And whatever our result ends up being would be the remainder, as if we had actually done the long division or the synthetic division, whichever the case might be. So 3 cubed is 27. 3 squared is 9, times 4 is negative 36, and then minus 5. When we combine these, we get negative 14. So what this tells me is that if I had divided that polynomial at the beginning of this example by x minus 3, my remainder would be negative 14. This will have implications in our next example, because we're as we go through today, everything's going to build on the previous example. So right now we're just trying to understand the remainder theorem itself, how it generates remainders based off zeros of linear factors. With part B, if we set this equal to 0, that implies then that x is equal to negative 2. So if we evaluate the function at negative 2, we are going to get negative 2 cubed minus 4 times negative 2 squared minus 5. When we simplify this, it's negative 8 minus 16 minus 5, which is equal to negative 29. So if we had divided the polynomial by x plus 2, our remainder would be negative 29. And this is the very next logical step in building upon the remainder theorem. It's what we call the factor theorem. And the factor theorem uses the remainder theorem. So you know how to use that. And what it tells us is it's going to be based upon the factors of what the result is of when we do the evaluation. So if you took if we take the remainder theorem and apply it to this next example, what we're looking for now is what is the value of the evaluation. If the value is 0, then what we are implying by that is that the factor we started with is a factor of the polynomial. If our remainder is something other than 0, then that linear factor or that linear equation is not a factor of the polynomial. So with example 2, we're going to start out the same way we did with the remainder theorem. We're just going to make an interpretation at the end of this. So we set this equal to 0, and that implies then that x has to be positive 1. If we evaluate the function at positive 1, we're going to get 2 minus 1 plus 2 minus 3, which does equal 0. And because it equals 0, what this tells us then is that x minus 1 is a factor of the polynomial. So that is a factor of f of x. We can do the same thing with part B. We set this equal to 0, which implies then that x has to be negative 2, and we evaluate the function at negative 2. When we evaluate this, we get negative 16 minus 4 minus 4 minus 3. And when we simplify that, we get negative 27. Because that does not equal 0, this is not a factor of f of x. Okay, so we're going to keep this factor theorem in mind because we're going to look at Descartes' rule of signs next. And then after that, we're going to build and kind of combine these together with Descartes' rule of signs and how to find factors of polynomials. So with Descartes' rule of signs, again, example is probably the easiest way to show you how this works. You can read the theorem if you would like, but it's easiest just to see it put to use or put to a practical example here. And what the Descartes rule of sign tells us is, 1, it helps us find the possible number of positive real zeros that a function may have. And then we do a simple evaluation process, and it also helps us then find the possible negative real zeros that a function may have. And all it is a matter of counting the number of sign changes. So the first thing, you take your given function, and you're looking for the possible positive real zeros. And this is just the number of real zeros, not the actual zeros themselves. So the positive real zeros. And we just take our given function and we count the number of sign changes. So we start out negative and go to positive. So there's 1, positive to positive. Positive to negative is our second sign change. And so this has 2 or 0 positive real zeros. And the way that works is we count the number of sign changes. If the number of sign changes is greater than 1, then we reduce that number by 2 until we can't reduce it by 2 anymore. So with this particular case, we had 2 sign changes. We reduce that by 2, we get 0. We can't reduce 0 by 2 any further. So that means we have either 2 or 0 positive real zeros. Then to look at the negative real zeros, this is where I said we do a simple evaluation, and then we count sign changes again and do the same process. But what we do is we replace x with negative x simplify the expression, and then we count the sign changes. So we have positive to positive, positive to positive, positive to positive, positive to negative. We have one sign change. We can't reduce 1 by 2, so we can only say that there is a possibility of one negative real zero in this particular function. So that's the application for Descartes' rule of signs, and we'll use that here in example 3, where it says what possibilities exist for the real zeros of f of x equals 3x to the 7th, and so on. So for the positive real zeros, we're going to count the number of sign changes in the original function. And we go from positive to negative, so there's 1. Negative to positive is 2. Positive to negative is 3. And we have 3 sign changes. So we have 3. We can reduce that by 2 to get to 1. So we have 3 or 1 positive real zeros. When we want to look at the negative real zeros, we replace x with negative x. And we'll simplify this. If the exponent is odd, the sign changes. If the exponent is even, the sign will not change. And we're going to count sign changes again. So we go from negative to negative, negative to negative, negative to positive. We get 1, 2. So we have 2 sign changes. So the possible number of negative real zeros that exist for this particular function are 2. We reduce that by 2. We get 0. So we have 2 or 0. Now, just to avoid any confusion, let's say that you had, we'll throw something out there. Let's say you had 6 sign changes. So 6 sign changes would be 6, 4, 2, or 0. That's the possible number of real zeros you may have, either positive or negative, depending on which sign you were evaluating. If you had, say, 7 sign changes, you could have 7, 5, 3, or 1. You just keep reducing by 2 until you can't reduce by 2 any further. That's how this process works with Descartes' rule of signs. The potential rational zeros theorem is another useful theorem in making a list of the positive rational zeros that may exist for any given function. And the way that works is we just simply look at 2 numbers, and there's just a very simple either you can look at it as division or simplification process to generate this list of potential rational zeros. So the first thing we look at is the constant at the end of the function, which we'll call p, and then the coefficient in front of the highest degree term, which we'll call q. So in example 4, our value for p is 6. And we list all the factors of 6, and when we do that, we put a plus or a minus in front of each one of those factors. So the factors of 6 would include plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. And then we do the same process for our value for q, which in this case happens to be 2. So the factors of 2 are plus or minus 1 and plus or minus 2. And then the way we put this together is we take all of our values for p and we create a ratio of p over q. So let's first list all the values for p and divide each one of those values by the first value for q. So I'm going to make the entire list here. So it's plus or minus 1 over plus or minus 1, plus or minus 2 over plus or minus 1. And once we've exhausted all the combinations with the first value in q, we'll jump up to the next value in q, which is 2. So we start all over again. And the last last step is to reduce all of these to simplest terms. So 1 over 1, we're going to generate a list of potential rational zeros here. 1 over 1 is 1. 2 over 1 is 2. 3 over 1 is 3. 6 over 1 is 6. Then we have plus or minus 1/2. The 2 over 2 reduces back down to 1. We don't list duplicates, so we ignore that one. And then we have 3 over 2. And then 6 over 2 reduces to 3, which is already in our list. So what we have here is a list of 12 potential rational zeros that may exist for this particular polynomial. That does not guarantee that any one of these numbers is a zero of the polynomial, but this is a potential list that may work. The zeros of this polynomial could be irrational, or it could be all complex. But this is a good place to start to try to figure out what the zeros might be. And we're going to apply this now in example 5. So with example 5, we're going to put everything we've learned up to this point on this set of notes into this single problem. So the first thing we want to do is find the number of possible positive real zeros and the number of possible negative real zeros. So we apply Descartes' rule of signs first. So we start out with a positive 2, positive 11, to a negative 7. So there's one sign change. We only have one sign change, so that means we have at most one positive real zero. Then we want to look at the possible negative real zeros, so we evaluate the function at negative x. And when we do this, negative 2x cubed plus 11x squared plus 7x. Count the sign changes. Negative to positive is one sign change. Positive to negative, there's our second sign change. So we can have 2 or 0 negative real zeros with this particular function. The potential rational zeros, if you notice, example 5 is the same as example 4, so I'm not going to go through the steps of finding the potential rational zeros. We've already done that. What we want to do now, though, is apply the factor theorem. And so we're going to test different values from our potential rational zero list in the given function and find a value that gives us 0 as the answer. So I'm just going, since I told you that this is about the 5th time I made this video, I already know where I'm going with this. So just for the sake of argument, let's say we decided to first try positive 6. If I evaluate this function at positive 6, we find that it's equal to 780, which does not equal 0. So we know that 6 is not a zero of the function. However, if I evaluate it at negative 6, I do find that it does in fact equal 0. So that means I have a 0 of x equals negative 6, which is the same as saying I have a factor of x plus 6 for the polynomial. So here is our first factor, x plus 6. We can take that 0 and now we can use synthetic division to generate what is known as a depressed equation. When we say a depressed equation following synthetic division, it means we've taken our original function and we've reduced the degree of that function by 1. So we're starting with a cubic function, which means it has a degree of 3. When I do the synthetic division, what I'm left with is the depressed equation, which is a degree 2 polynomial. And here's the process in case you've forgotten from Algebra 2. We take our 0 of negative 6, and we're going to divide it into, using synthetic division, into the polynomial that we began with. And all you have to do is list the coefficients from that polynomial. So we have a 2, 11, negative 7, and negative 6. The way synthetic division works is we take this first term and we go ahead and bring it straight down. And then we just multiply. Negative 6 times 2 is negative 12. And we're going to add the 11 and the 12 to get negative 1. And then it's negative 1 times negative 6, which is positive 6. Negative 7 plus 6 is negative 1. Negative 6 times negative 1 is positive 6. Negative 6 plus 6 is 0. And we're finished with the synthetic division. What this does, I've mentioned before, this leaves us with what we call a depressed equation. We started out with x cubed as our highest degree. So now we have x squared, x, and a constant. So we have generated a new polynomial of 2x squared minus x minus 1. This is a quadratic that we can easily factor into 2x plus 1 and x minus 1. So now we have found the remaining factors of our polynomial function that we started with at the beginning of this problem. And we now can write the factored form as x plus 6, 2x plus 1 times x minus 1. And that's our factored form. And each one of these three factors, if we set them equal to 0 and solve for x, we would generate the zeros of the function, which happens to be negative 6, negative 1/2, and positive 1. So here are our zeros. And if you go back and look at our potential rational zeros list, you'll find that all three of these zeros are in that list. So this is the end of part 1. I'm going to get this one going and get it uploaded, and then we'll start part 2 shortly.